This is the intro to Rust and WebAssembly talk. Link here if you want to follow along. I also posted the link to the slides in the Slack channel, room 145, if you want them. Big thanks to the sponsors as always and all the organizers on Nerd Summit. I will preface this for anyone who's in attention to detail here. You'll notice my slides. I've tried to shift to lighter color slides for better accessibility recently. One of my social icons here, the GitLab icon, has a white instead of a cream color in the middle. And that sort of, to me, is a little symbolic of how I'm feeling about my slides this year. Unfortunately, the company I work for, Crossover Health, runs clinics across the US. And we've been kind of busy the past few weeks. So I'm going to do my best to do this session justice and go through Rust and WebAssembly. Near the end here, it's going to be a little bit more informal and impromptu as I go through some of the details and examples on things. So anybody wants to reach me pretty much anywhere at Pete Johansson, you can find me, Twitter, GitLab, GitHub, etc. Reach out, connect. Love to connect with folks. So gonna dive right in, basically sort of a story in three parts here. First talking about Rust, then WebAssembly, very briefly, honestly, and then the power of the two combined for the last part of the session here. So diving right in, just sort of what is Rust? And I went and checked on Rust's marketing website for this when I was preparing my slides. And I found the biggest, most hand-wavy description ever as languages go, a language empowering everyone to build reliable and efficient software, which honestly doesn't really actually mean all that much to me. But they do then go on to talk about a few of the specifics of what that really means when it comes to the language Rust. So in particular, one of the strengths of Rust is its type system. So the type system, sort of the foundation of everything. Rust is a strongly typed language. It is not a Ruby or a PHP or a Python. And so, compile time, it is a compiled, strongly typed language. So when you see some Rust, you've got the basics. You've got things like Booleans, and you've got unsigned integers of various sizes, and you've got strings of various kinds. And we'll talk about the details a little bit, but fundamentally, there are some very simple basic types, what you would normally expect, literals of those various types as well. Here in particular, I am being very explicit about my types. There's actually a lot of type inference to save you a lot of finger typing on a lot of these when you're actually implementing things with the language, but I wanted to be explicit for the examples here. So basic types are what you would expect from a language. You then start getting into things that are a little more detailed and really help unlock a bit more power of the language. For anybody familiar with C or other languages, there is an enum type that you would expect, like as an enumeration of possible types in that. So we can consider a point type to be, a point type is either dot, circle, or square. So there are enums, and we're going to see more powerful enums coming up here after this. But the basic enum you would expect, a set of possible simple values is there. Structs are also supported. This would be similar to structs in C languages. They're not classes, but hold a set of values with names of certain types. So a simple point you can imagine of having an X, Y, the location, as unsigned integer values, and the type of point. Let's say a point type of type we talked about before. And so pretty simple to create these things and look at them. You can see I'm defining some const origin value where an origin is a point at 0, 0, and the type here is a dot. Now you can maybe forgive me for not modeling this perfectly, but the spirit here is you can create different enum values. You can see here with the double dot syntax, and you can create structs by specifying the various fields of the structs. So enums and structs are there. But this example really is a very simplest of enums. There's much more power to enums if you look at the more nuanced way that you can use enums, where enums not only can be a set of possible contained entries or types within the enum, but each of those types can actually have its own set additional values or details linked to just that type in the enum. So we can imagine, evolving the previous example I had here, that you could have an enum of some possible shapes and then define a circle shape as having a radius. But a radius makes no sense when it comes to a square or a rectangle. And so for the other shapes, you can define those properties that are only relevant and would only be stored with an example of that particular type in the enum. So here, I've got a 4 square here. I can define a square with a size of 4, and I don't need to define a radius. I don't need to define the width and the height like I would with a rectangle. And so enums get much more powerful when you can unlock the fact that they can very easily model with a richer way of doing so different kinds of data. And so I can very easily have a collection of shapes, and those shapes only contain the details relevant to them. So you can kind of think of this as synonymous to maybe sort of a parent class and then subclasses, where you might have some interface like shape, and each of the subclasses of that interface has, the details that they need, the radius for a circle, etc. So that is the way you can unlock some very powerful, strongly typed behavior in Rust, is using enums, where the enums, each of the values in that enum has the details it just needs for that particular entry in that enum. So the other thing that Rust has is generics. So if you've ever worked in strongly typed languages like maybe C#, for instance, the concept of generics comes up pretty quickly, where sort of a simple canonical example, and this is a type that's found in the core of Rust, the language. You can imagine you might have an option type, where an option type, the enum is either nothing, you've got nothing there, or you have something there. So this is also one of the ways where Rust has this built in, and it's the way that it handles null. There is no concept in the safe code in Rust of null. It is not something that the language really has as a feature in safe code. There's a way to do unsafe code in Rust, which does not have the same guarantees around safety. But the way that you represent not having a value is very explicit and intentional in Rust. And most of the time that means using the option type, which is built in, but I've redefined it here, where an option contains some sort of value of some type. And so we don't need to redefine an option string, an option U32, an option struct. We can just define the generic option of T, and that generic parameter is the kind of thing stored when you have a sum value. And so, for instance, here I've got a zero sum, yes, a lame joke, I admit it, where it is an option of type U32. The generic parameter is now actually, for this instance, specified, and it's an option : sum of 0. Similarly, that option U32 value could have had an option of none, and it would be a none value. It didn't have any T in it, but it's still of type option U32. And so those are the basic building blocks of the type system that help give one part of the big collection of features that help give Rust some of its powerful safety and strong typing features that let you write very fast code that is also safe and will work, because I know this thing is of a certain type, and using generics I can then build a bunch of reusable blocks on top of that type system. So with types out of the way, you can then go on to the next sort of major feature you need from a language, which is functions. And so Rust is not object-oriented. So I'll talk about functions a lot, and there's a lot of different ways to use functions when combined with traits to get sort of similar to an object-oriented type of behavior, but it is not object-oriented. And so functions are pretty straightforward. They take input parameters and they output a certain response, single response value. So you can see here pretty basic functions here. A double function. It takes in a U32 and it returns a U32. Similarly, you can define like a Fibonacci function. It takes in a U32 and returns another U32. You can see here I'm showing off some of the other language features here. There's really strong pattern matching and match support in the language. I'll show a little bit more of that in the destructuring stuff that we talk about in a little bit. But here you can see I can match in a value in the input, And if I have it either a 0 or a 1, return an X, the value itself, or I can perform some other calculation on the input value. So the fib of the value before plus the current value, for instance. So basic functions. So you'll notice here, though, that the definitions of these are strongly typed. So it's very clear, like my function has to have the type specified for the input parameters and the type of the return value. So already you might be thinking, holy cow, this sounds like I'm going to be typing types everywhere. But the reality is, one of the nice features about Rust is the types at the edges are required to be strongly typed and very explicitly specified, but the types internally less so. And so the language has the concept of type inference, and so it can infer what the types of various values are within a function. So even though we might be very explicit about the typing of our function itself, internally within the function, we don't need to worry about it as much. And so you can see, for example, that the is_gt is greater than is pretty silly. Normally you wouldn't store that to a local variable when you're writing modified code. But the reality is, by is_gt, that local variable is a type Boolean, but I didn't have to type that. I didn't have to be explicit about it. Rust could infer that for me so that I'm not typing every single one of my variables internally while I'm doing this work. And the reality is that very often you won't want to do that because writing code this way makes it easier to refactor later. And so internally here, I can not type any of my local variables. And as long as when we are working with the edges of our function, the input parameters and the output, it matches, Rust will be happy. So I didn't explicitly have to type my ret value in here as of type string. But if I tried to return some other type at the end of my function and I went to compile this, the Rust compiler would yell at me and say, I'm sorry, you told me that this function was going to return a string. You're actually returning an integer, a U32. So I can't compile this. It doesn't make sense. So the edges are enforced, the constraints that you said what your function would do, but internally it's nicely type inferred. So you don't have to add those types to every single variable that you're declaring. So the other nice thing that is with function is this concept of self. And so you can do what's called implement additional functionality around an enum or a struct and attach functions to those instances. So this is the closest thing you can have to something like an object returning language where you might call an instance method on an object. Although strictly speaking, that's not truly what's happening. So if you are familiar with Python, this might feel very, very familiar, where we can say, I'm going to implement option T, and I'm going to define some function that takes in self as the first parameter. And Rust lets you now use a calling convention where I can use a dot syntax and call the function on an instance of that type. And so because I implemented the isSum function, with self being the first parameter, now when I have some instance of some T, whatever that T is, I can call isSum on it. And so this is a really nice way that you can add some functionality that's available on your types, make it easy to call them on those instances of those structs without typing it the reverse notation, as in like calling isSum and passing in your first variable as the self. To make it feel much more like an object-oriented language, but it is not, strictly speaking. It's just another function call where that first parameter is implicitly added as the first parameter of the function that you defined. So there are even ways with traits, which unfortunately I did not get into a lot of the details of traits and how to implement them with the time I had in this call. But there's this concept of traits as well, where a trait would be like comparable, or a trait might be equals, like this can be compared, or a trait might be format, where it can be displayed as a string, where you can use a similar approach with an implementation of that trait, and then you define the functions linked to that particular struct or enum, that type. So that gets you type system plus functions. You've got a lot of behavior now, a lot of functionality you can get from Rust, the programming language. Another nicety, in addition to things like type inference, is this concept of destructuring, which a lot of functional programming languages have. JavaScript has just started having it not too long ago, but with strongly typing, with Rust, you get a lot you can do when it comes to destructuring, and you can use that behavior in a lot of different ways. So we can do things like internally within a function, we can destructure a struct. So I've got my function point type, which is a pretty lame function. You normally wouldn't write this function, but it's the best example I could quickly come up with here, where the point type function takes in a point, which is the struct that we defined earlier, and returns this point type enum, right? And so to do that, you can assign, like I did my little local variables before, but I can specify that I'm going to pull out the values from this point type into some local variable. So I'm destructuring my point object into some of its pieces, ignoring some of them, prefixing them with underscores, and taking one of them, which is the one I care about, and I'm returning it. Point of note while I'm here, you'll notice that there's never been a single return statement yet in any of this. Rust has implicit returns with the last statement in a block, which doesn't have a semicolon. It takes some getting used to. It very much so does. And so you can see here that my point type function, I didn't have to specify a return type with a semicolon. I literally just put type in the last line. Feels sort of Ruby-esque to me. But the difference between a semicolon version and the lack of semicolon version, I'm curious how they decided to design the language this way, but when they did so, it lets you still write pretty succinct code while still having all of the benefits of nice, strong type enforcement and all of those things. So shifting back to destructuring, you can also destructure in match statements, for instance. So if I take in a shape, let's say I have a function where I want to increase the size of a shape, and a shape is this more complex enum, like I gave examples of earlier, where a shape is one of possible 3 values. A shape is a circle, a square, or a rectangle, right? I can write a function called increase that will take a shape and increase the size of that shape. Now, you probably would want this more nuanced, or like how much, some factor or whatever, but fundamentally I can match on that shape and destructure into the component pieces of each of those possible enum types. So when I want to destructure a circle, I can pull out the radius value from a circle. And I know that I define my type, my enum type as a circle has one value as a U32, that's the radius. So I can easily destructure my circle and pull out the radius value from it to then return a new instance of a circle where the radius has been doubled. I can destructure my square into one value, which is the size of my square in F, let's say, return a square that's doubled. Similarly, I can destructure the 2 values on a rectangle, the width and the height. And once I've extracted those values from that enum, I can now use those for further calculations, whatever I want to do, including in this case, I want to double the width and double the height of my rectangle. So destructuring lets you easily take apart some of these complex types into their smaller pieces so that you can use them. So one of the other guarantees that helps Rust be type safe and fast is around immutability. So I mentioned that there's no null value. That chops off a whole set of possible bugs, right? Immutability is another way that Rust is very clear about how various values will be used, whether they are modifiable or not. And so to give you an example here, if I define a point, P1, and I specify its X and its Y value and a type of point type dot, if I then try and update that particular point, Rust will not allow it. It will enforce that you can only modify mutable values. And so by doing so, one, it can behind the scenes do a lot of performance improvements within various scenarios, but it also can make sure that you don't have multiple people trying to modify things at once. which is another whole class of the kinds of bugs when you're writing C or C++ or those other languages that can cause some serious problems for you. And so there is very clearly the concept of a local variable that is either mutable or not. When linked with borrows and lifetimes, can help you very clearly enforce that you can never have a mutable variable passed around where multiple people might try and, like from multiple threads, let's say, try and mutate that thing at the same time, which we know is a source of all sorts of weird threading and concurrency and race conditions and those sorts of things. So this is one piece of the puzzle where Rust will help remove the ability, as long as you aren't using unsafe code, to introduce those whole classes of bugs that you can't write in safe Rust code. It doesn't allow it as a language. And so Rust, very, very, very specific about mutability. You cannot modify something unless it is intentionally a mutable version of it. And when it comes to the lifetimes and borrowing, it then helps make sure that only one person has a mutable borrow to something. So most of everything we've seen so far has been values, value types. They are one instance of this thing. I can maybe make copies of it, but they are local and stored locally. The other piece, which this is where I will pause and say, this is the one part, if you decide to learn Rust or if you already are using Rust, that will catch you up, that it will hurt your head, that it will not be pleasant at times. And this is still something I hit on a regular basis. I will willingly admit it. One of the trade-offs with deciding to use Rust is you will need to deal with lifetimes and ownership type issues. And sometimes those make it feel harder because the language itself is keeping you from doing things you might have gotten away with in other languages. And the way they got around that is with things like garbage collectors or other approaches that solve the problem in a similar way, but might make it not as fast of a language. So Rust has tried to strike a balance between a very fast performant language that also is convenient to use and gives you very strong guarantees. And the lifetime ownership stuff is one of those areas where the balance there has resulted in a language feature that can be challenging, and I will willingly admit that. So I've been hand waving for a little while, but so lifetimes exist and they are usually tied to borrows of things. And so in a previous example, I gave you an example of a string. There are various lifetimes, one special one called static that define how long something lives for. And so in the previous example, we had these inputs to functions and we had outputs to functions and we had local variables contained in the middle there. And all of them are local or input and output variables that it's easy to understand their lifetime and their scope and how long they will live. But sometimes you need to pass around what in a language like C would usually be called a reference or a pointer, but in Rust are called borrows with a certain lifetime. So we can imagine that strings, like a set of characters, might be actually hard-coded in your program, right? So I literally have this literal testing, which that's when I compile Rust, it's literally going to be compiled in the program. It's going to be some point in memory that contains those bytes, and it is so-called static lifetime because those same bytes in that location of memory will live for the entire lifetime of my program. They will never go away. They will never be modified because this thing is not mutable. And I can easily refer to this static string anywhere in my code, and I'm happy. But there are other times where we might have something which is a string that came from some bytes from some HTTP request into our server, and the lifetime of those bytes needs to start somewhere. We took them off the network stack, and at some point we need to let go of them. We need to free that memory. And so the solution here with Rust is the concept of lifetimes. And so the tricky thing here is most of the time those lifetimes are controlled by callers and not so much my code that's worrying about them. So they tend to live on the edges where the lifetimes actually get created for these things. So the low-level network code is the one that's like reading the bytes from off the network stack. And that's where that first ownership of those bytes lives. And everyone else is like processing those bytes from the web, your web request that's like reading the body of your JSON request body. It's just borrowing. It's just referencing that piece of bytes that is in memory that the network stack gave you for now until you're done with it. And so oftentimes we implement functions where there's a certain lifetime for our inputs that we care about. And usually the language does what's called elision. I have no idea how to pronounce that properly, where it will get rid of them. Like you don't need to worry about the specifics of it. And so you can pretend they aren't there. And so this is a nice way that often you don't have to spend as much time thinking about lifetimes until you do have to start thinking about them because you have some need for it. And so whenever we see this ampersand here, that's a borrow. So this function length isn't actually getting the bytes of that string passed in. It's getting a reference, a borrow to those bytes that it's going to use during the duration of that particular function call. And so during the time when we are in this function body, I'm the one that has a reference to this thing. I know that string will be there because of immutability. I know it won't get changed, and I can start using it and working with it, and there's no other thread that's going to change the bytes in the middle of my call or anything like that. But the reality is, behind the scenes, there's really a specific lifetime. This little sort of looks like generics, apostrophe A, that is a specific lifetime for that borrow for that string, because it might be static. It might be some static string that's compiled into my program, or it might be some string that, a set of bytes that came off of our network stack from our OS. And we've just got it for now. And I'm saying in the middle of my function, I'm the one using those bytes from that, the network stack right now to inspect the size of that string. So elision hides a bit. Most of the time, anytime you see that ampersand, there really is a lifetime to that thing. Somewhere, somebody has let you borrow that for a certain amount of time. And at some point, you need to give it back. Somebody needs to be done with it whenever there's a borrow like this. So for the lifetime of this len function, that string s is borrowed. No one else can use it right now. I'm using it because I'm looking at the length of this particular string. So similarly, there are constraints around borrow. So I can only borrow a point oh, I totally didn't update this slide with the borrow stuff. I'm going to circle back. I will send out the links to this later afterwards. You can only borrow things as mutably or immutably as well. So just like Rust enforces that you can't change a point that is not mutable, you can have a concept of mutable and immutable borrows, and you can only ever have one or the other. And this is how you can enforce that if I've borrowed this right now to inspect the length of it, no one else is going to be able to change this while I have my borrow. And so it is really confusing, and I could literally probably spend an entire presentation on it. I wanted to give everybody a taste of it. I can send out links later to the nitty gritty. There's a whole section of it in the Rustlang book. But it is something that you will have to learn, and I could not do it justice, unfortunately, for the length of this presentation, but I wanted to give everybody a taste. So borrows and lifetimes, and they are one of the reasons that Rust gets to be as fast as it is and have the guarantees it has. So that's Rust. And I didn't give a lot of examples because I wanted to talk about WebAssembly and then actually dive into some real code that uses all these features. So that's the first half. That's Rust. So this is Rust plus WebAssembly. Let's talk about WebAssembly. So WebAssembly. So WebAssembly is low level. And this is where I'm going to probably surprise everybody. This is my only slide where I'm going to show any WebAssembly code. So WebAssembly is a stack-based linear memory virtual machine with big air quotes that is implemented by all major browsers. And so you can think of this as similar to maybe a virtual machine like using VMware, only it is an imagined virtual machine that is implemented at the very low level by all of your browsers. And so it's stack-based, so you can see here that we've got this function add that has 2 parameters, and then we get to push them onto our stack, and then we call this I32 add, which is going to pop the things off of the stack and perform some math on them and push them back onto the stack, let's say. That's really low level. And I don't think anybody on a front-end web development wants to spend the next 20 minutes talking about what is effectively writing assembly, right? So you can think of this as like 8086 assembly for your processor, only it's low level you know, operations that your browser can implement. And the nice thing is browsers can very nicely translate this pretty directly to very fast, efficient operations on your actual processor on your computer. And so unlike a higher level language like JavaScript, where there's a lot of layers between your JavaScript objects and your DOM items and the equivalent CPU operations, WebAssembly nicely maps to very low level fast operations on your computer. And so much like Rust, the compiler can normally spit out, you know, x86 code, you know, 64-bit code when it's compiled natively, we can make a lot of different programming languages, Rust WebAssembly, Rust Go, for example, spit out this kind of low-level code instead, only it can run in all of your browsers. And so this is where we can start writing not JavaScript, but, you know, writing Rust, but have it start being executed by our browsers that support WebAssembly, which at this point is all the major ones. IE11, I'm fairly certain supported it. Chrome does, Firefox does, Edge does, Safari does, you name it. And so that's the only slide I'm going to show you in WebAssembly. You could dive in on the specifics if you want to, but you can really think of it as like, I'm not going to learn 8086 assembly and write that to write code for my laptop. I'm going to learn C, or I'm going to learn Rust. So that's the last slide. I'm literally not going to show you more. I just want to talk about how you can take Rust, the really cool language, and turn it into code that you can execute and have your browser load and run. So Rust, they often use crabs for, WebAssembly, they often use webs for, equals love. So let's talk about what that really means. Okay, so we want to take this Rust, this crazy language, we want to run it in our browsers. Our browsers understand this weird low-level stack-based linear memory thing. So let's first talk about the basic tools. So Rust has this very convenient utility called Rustup that lets you install various versions of Rust, install various extensions, other packages, you name it. One of the things that you can do is you can install other targets. So most programming language, you might install like, oh, I want to build for both ARM and x86, right? So I'm going to install an ARM target and cross-compile to ARM, let's say, right? In this case, we want to target WebAssembly as our target, and it's not a particular convention, you know, Linux new or Win32 or anything like that. And so Rust just has yet another target, like what kind of code should I output? What sort of, you know, what should my final target be for the resulting compile? And in this case, it's, I want to compile this to WASM32, 32-bit WebAssembly. And so pretty directly, I showed this, you know, Fibonacci function that I wrote earlier. I can take this code and I can run Rust C with a target of WebAssembly, unknown, a C level dynamic lib, and I can take some fib.rs and I can compile it and I can make it work. So in the interest of time, I will leave that as an exercise to the reader when looking at my slides. It's pretty straightforward to do that. And the cool thing is I can then take that, and my browser has all this cool built-in functionality to then call it. So I can fetch my fib.wasm, which is what's going to get compiled from this from the Rust code into WebAssembly. I'm going to turn it into an array buffer. Now, normally you won't end up doing this. This is what's going on behind the scenes. I'm going to fetch it. I'm going to turn it into an array buffer, a raw buffer of bytes. I'm going to call WebAssembly instantiate, like actually turn this into some WebAssembly you know, module. And I'm going to take that WebAssembly, and from those exports, I'm going to call .fib on it. And so I can very easily, if I want to, write just low-level, you know, code that functions on integers and bytes, and that will work. But the reality is, most of the time, we're not writing Fibonacci sequence code, and we won't want to optimize that for our browser. We're doing higher level work, right? And so that's the foundational building block. But with that building block in place, you can build all sorts of cool stuff on top of it. And so let's talk about some of the power tools built on top of this very low level virtual machine sort of behavior. So one of the first things you immediately want to go to is like, okay, that's nice, but I want to draw to a canvas. I want to call console.log. I want to do all these things that I normally do with code that's running in the browser, right? First step is something called WASM bindgen. So WASM is short for WebAssembly. BindGen is a binding generator, right? So WASM bindgen, pretty cool, amazing tool that the Rust folks have built that lets you both import JavaScript things into Rust and export Rust things to JavaScript. So that looks like this in the Rust code. So I can, these are Rust macros. I can tag with this WASM gen macro, hey, I want to pull these things in that are defined elsewhere in my system, like the standard window alert function. And I want to export a function called greet that I can call from JavaScript land. And so with WASM bindgen, I don't have to work on integers and low level, like stack-based virtual machine stuff. I can define higher level behaviors around strings and JavaScript objects and things like that. And so we do two things. We can export from Rust. So all of those structs and classes I was showing you, those functions that you wrote, the strings that you've got, you can export everything that you've written there out so that JavaScript land can easily call that. So I can write really crazy cool Rust code, and I want to tie it into my React component that I've got. I can use WASM bindgen. It will generate definitions of stuff that I can start calling from my standard React components, from my hyper app, Vue.js, however you want to do it. It exports standard, what I would normally expect JavaScript stuff, and add a bonus, it'll export TypeScript definitions of that stuff for you too. So if you're doing strongly typed TypeScript for everything you're doing, you can nicely integrate that with the stuff that's coming from Rustland. And then on the other side of things, I can import from JavaScript. So in my low-level Rust code, I can get type definitions for all my DOM stuff. I have a window, I have a canvas, whatever. So I can import from JavaScript land all those things, and even more powerful web APIs like WebGL or Canvas. So I can start writing code that can be very fast, very efficient, compiled to a memory efficient, cool programming language, and it can be what's running the code to do a bunch of WebGL automation or write to your canvas. So you can use a really powerful language that side effect, hey, you can write it so it can output native code and have a 3D game that runs on your desktop and in your browser. There are frameworks that do that. You're leveraging this sort of power. And you can import user JavaScript. So any of your normal JavaScript objects that you've written, you can then make calls into them from your Rust code if you want to. So that's the general functionality of WASM bindgen. And so that same group has done the hard work of actually doing the binding generation for all of the standard web platform stuff you would want. And so there is a crate in Rust parlance called WebSys that has the definitions of all of the normal stuff you would want to talk to from JavaScript code, but you can do it from Rust code. So I'm going to add a WebSys dependency to my code, and I'm going to enable the types so that I can access documents and elements, HTML elements, nodes, and windows. Now, for reasons of efficiency, you can turn on all the features, but then you're going to compile a bunch of Rust code you don't need, or just the features you need so you can keep your final compiled Rust to be streamlined. And now I can start using all of the normal stuff that you want from JavaScript DOM APIs in your Rust code. So I can define a run function in my Rust code that will grab the current window, it will grab the document from the window, it will grab the body, and then it'll create an element in that document and set the value to it and append it to the body. So now I am writing low-level efficient Rust code, and where I need to, I can interact with the web that is the web. So once you have that piece, which does low-level generation, you also want to make it really easy to actually do all of this. So Webpack is a tool that lets you easily generate an NPM package if you just do a package. It also has very nice integration for integrating Rust and WebAssembly into your standard Webpack pipeline. So I can write a bunch of Rust code in this crate right here. I've got my standard JavaScript or TypeScript code that's doing all my React components or my view or whatever I'm doing. And WasmPack will let you pull in the Rust pieces seamlessly into the rest of your build pipeline, and it all sort of just works. And so you can very easily do one simple npm init with the Rust Webpack template, and it'll generate you an awesome starter that's got Webpack, it's got Rust, it's got WasmPack for all of it. So you can start doing all of this, you know, JavaScript calling it a Rust, vice versa, and it all will just work. So if you generate one of these things, you got a pretty basic like mashup of the two things. You've got your Rust, you know, cargo definition, and you've got your JavaScript len package.json, package.json. Under source, you'll find all of your Rust code. Under JS, you'll find all of your JavaScript code, and you can hit your ground running and customize from there. So there are also a few even cooler things that are taking it a step further. There's a pretty cool framework called U, which is basically taking it one step further, like, hey, what if we took React out of the picture altogether, let's say, and we did all of that kind of work in Rust. So we take the primitives like, oh, I can access a document in a window, and let's actually write the equivalent of like React components, but actually write those things in Rust. And so you can pretty easily define some basic things, so we structs like we talked about before, and enum for the possible message types. And then you can actually implement a component, the component API for your app. You create it with some data, and then you've got two simple functions, an update function. Here's what happens in reaction to a certain click or a certain activity from the user, in which updates our state, and then a view function that takes your current state and turns it into the DOM. So for anybody that's done like Elm, for instance, if you've used Elm at all, which is sort of a very pure function or hyper app where you have an update loop, and then your render is sort of this equivalent of like a render function for whatever the current state is in React land. You can do that, and that's it. And then you start your app. So there's even people that are pushing this even further and thinking about using Rust for the whole start to finish of your application. So that's a whirlwind. It's a lot to cover. So I do have at the end here, I have a real world example a little while ago. I was really excited for this. So I wrote a classic sort of worm game where the worm will move and you can eat the dots as they show up on your screen. All of the actual game logic is in Rust, and even the code that draws to the canvas in Rust. So you can play around with that. And I have the links to the slides here to give you a very, very quick taste of the worm game here. And it's bare bones UI. This is not gold plated here. I can play my worm game, and eventually there'll be a little red dot that will show up here, and I can eat it and try and eat it, and my worm gets longer. So all of that is written as Rust code. There's no JavaScript for any of the game logic here. It's just Rust code running by hyperware. So I have, oh, I lost my slides. I meant to go back here. I have a whole 2 minutes for questions. So I don't, host, if you could help out, if anyone has any questions for me, I would love to answer them in the, I'm sorry, 1 minute that we have left. Can I unmute all? I can unmute all.
Yeah, go right ahead.
Questions? You may be unmuted on my end, but you may need to unmute yourselves, everyone, if anyone has any questions to ask. All right, then. Well, thank you everybody for coming. Hopefully some of you enjoyed it, and hopefully some of you can check it out and ask me any and all questions you might have as you dive in and start learning it.
Sorry, I had a question. Can you hear me?
I hear somebody just barely, very, very quiet.
Okay, I'll try to speak very loud. Don't know why the mic's not working. Can you do breakpoints?
Maybe you can type your question in the chat and I can find it that way.
It is in the chat.
Let me find the chat here. There it is. Can you do breakpoints? That's a good question. You certainly can when you're doing native Rust code. All I've done so far is use various debugging techniques to output to the console, and I've gone with that strategy. I am fairly certain that there is source maps that get built when you run in debug mode that let you then map and go in and set breakpoints that way. To be honest, I haven't had to do it, but I seem to recall seeing that there is source maps that get implemented that let you do things like breakpoints and go about it that way. All right. Well, I'm going to try and be a good presenter and preserve the time for the next person. So thank you, everybody. Hit me up on the Slack channel if you want, or on Twitter, and have a good rest of Nerd Summit. Thank you, Gabe.